So good morning, students. We have been discussing the natural convection in the last class. So, in the last class, actually, I have concluded the discussion on natural convection. The various cases that are there in natural convection are solved in the last class. Now I will just brief you about various cases there. So here you have this natural convection, which is also called as a free convection. So in this, we'll be having a vertical surface case. This is the most general case. And in this, you will have again the laminar and turbulent cases. Okay, based on the case that you are getting, you'll be choosing the appropriate NU formula. Based on the formula chosen, you'll be finding out the H value. Okay, in turbulent, this is the formula, most generally used formula, or this can also be used. Likewise, you'll be choosing the formulas in case of a flat plate. So first thing is here, flat plate, and this plate is actually vertical in the case of free convection. So that is the first case. In this, you will have laminar and turbulent. And moving further, you will have horizontal plate. This is the next thing. In this, you will have these cases here, as you can see. And moving on, you will also have cylinders case. This also we have covered. And you may have the spheres case and rectangular cavities case. All these things are not covered. Okay, you are expected to solve it by yourself. Okay, the point here is majorly you will be getting questions based on the vertical plate itself, vertical surface itself. So this is covered enough. So that ends our discussion on free convection. So moving further, I have here a procedure for solving the problems in convection. Okay, so in convection, what to do is basic thing is to find out the problem in which particular case it is falling. The first case is forced convection internal flow, second case is forced convection external flow, third case is natural convection case. Among these three, which case the given problem is falling, that itself is a very important thing. Okay, if you fail here, if you fail in finding out to which case the given problem belongs, you will actually fail completely in solving the problem. So this is very key step. The first one is very key step. So how do you find whether the flow is internal flow, external flow, or a natural convection flow? Okay, what is the basis for that? So when it is coming to internal flow, you will have words like the pipe. You will have the words like pipe, tube. Okay, inside the tube. Okay, these things are given. Okay, here in case of the forced convection, you will have over the plate, over the tube, like that. The key word is over the here. Okay, this above also can be used here. Kind of words, these are the key words. When it comes to natural convection, you will have quiet or quiescent or something like natural convection itself or buoyancy forces itself. So these kind of words are there in the problem. You have to carefully look at what are the cases, what are the keywords that are there in the problem, and find out which case it is. After that, you have to find out the material. Actually, I have missed that material here. Find out the material in each and every case. Okay, what is the material? In each case, you have to find out. After that, you have to check for the temperature at which you will take the properties, you will evaluate the properties. In case of forced convection, you have to take the bulk mean temperature, internal flow bulk mean temperature, external flow film temperature, natural convection film temperature. So what is the difference between the bulk temperature and film temperature? In bulk temperature, you will have the fluid temperatures. This is a fluid temperature. this is also a fluid temperature. Whereas here, this is a wall temperature, there is a solid temperature, and this is a fluid temperature. So in bulk mean temperature, you will take the average of fluid temperatures, whereas in film temperature, you will take the average of film temperature and the wall temperature. So that's the thing with the temperatures, the bulk mean and the film temperatures. Next thing to do in the problem is find out whether the flow is laminar or turbulent. How do you find it in case of the forced convection? You take 2300 as a critical Reynolds number. Okay, if it is falling above this, that is turbulent, below the laminar. Okay, 5 into 10 to the power of 5 in case of flat plate external flow case. Here you have to take the Rayleigh number, not the Reynolds number. And this Rayleigh number is a product of Grashof into the Prandtl, and that will be 10 to the power of 9 here. If it is falling greater than 10 to the power of 9, so in case of natural convection, Rayleigh number has to be calculated, that the product of Grashof into Prandtl has to be calculated, and we have to check for 10 to the power of 9. If it is falling below 10 to the power of 9, that is the case for laminar. If it is greater than 10 to the power of 9, that is the case for turbulent in case of natural convection. When it comes to Nusselt number formula will be depending on Reynolds and Prandtl in case of the forced convection, internal flow or external flow, both the things is like depending on the Reynolds and Prandtl. In case of the natural convection, Nusselt number is depending on Grashof and Prandtl. Okay, that is the thing here. The characteristic dimension is taken as D. Here, the characteristic dimension is taken as L in most cases. So based on the case, you have to actually follow. Okay, L or D, anything can be followed in case of natural convection. Even in the case of the forced convection external flow, Nusselt number will be equal to HD by K, can be taken when you are taking the flow over pipes. Flow over pipes is taken. Flow over pipes. Taken, it is HD by K. Anyways, that's a special case. Okay, so based on the case, you have to take the HL by K or HD by K. That's the thing here. So with that, I'm concluding the summary also on these three things. This is very important. If you understand this process clearly, you can solve any given problem. So moving on, what we have next in this unit 3 is the dimensional analysis. In dimensional analysis, you must be knowing this something called as a dimensional formula. Something called as a dimensional formula. You must have studied in your school itself. So tell me, what are the primary dimensional terms, or you say primary units in general? Okay, what are those primary units?
Mass length times
Mass, and then length, and then time. These are the most basic things. Okay, along with this, here in our discussion of heat transfer, we will add temperature and the heat also to be the primary units for the sake of simplicity. Okay, actually speaking, in reality, only these three, or even the temperature also can be the uh, primary unit, but heat cannot be the primary unit. It is actually a derived unit. Okay, you will use all the primary unit to write the unit for this heat. Okay, but heat will be repeating so many times in our heat transfer analysis. That's why heat is also taken up here. So what is the unit for the mass? So what I'll be doing is I'll be writing the unit and dimensional formula for all these terms here. So tell me what is the unit for mass? SI unit is kg. Dimensionally, how I will show it? I will show it with capital M. Coming to length, what is the unit? SI unit is meters. How I show it here in dimensional formula? L. You must have studied all of these things in your lower level classes. That's why I'm going a bit fast. So this is time unit is second, and the dimensional formula is T. Temperature unit is Kelvin, and the dimensional formula is theta. Heat. What is the unit of heat? Somebody tell me what is the unit of heat? Unit of heat is joule. Okay. Unit of heat is joule. So joule you can take here. What is the dimensional formula for joule? Can somebody tell me? Express joule in basic terms. Okay. Joule is nothing but Newton meter. Newton meter, how you can express Newton in terms of basic terms? Newton is m into g, m into meter per second square. So this meter can multiply here, kg meter square plus second square per second square. So the kg unit is m, and L kge dimension is m. The meter, the dimension is L square. I have to put there. Second dimension is T to the power of minus 2. So this is how we will take the dimensional formula for all these things. So these basic things you remember. Keeping these things in mind, we will have something called as Buckingham's pi theorem. Okay. So before we go to Buckingham pi theorem, I must tell you what is the dimensional homogeneity is. Dimensional homogeneity. Okay. For this, let me use the Bernoulli's equation. Okay, I'm taking this example because this is very easy example to understand this dimensional homogeneity. Somebody tell me what is Bernoulli's equation? Am I right? Is this the Bernoulli's equation? Yes, please tell me. Is this the Bernoulli's equation? Yes, it is. So if you look at this, what is the unit for the first term? What is the unit for the first term? What is the unit for this term?
Meter,
And what is it? Meter,
meter.
this meter, and meter. What is the unit on this side? On the right hand side, it is also meters. See, you can add rupee with rupee. Rupee should be added with rupee. This is correct. If you are adding rupee with a dollar, this is wrong. Okay, so this is wrong. This is correct. So if you add a rupee with rupee, that is proper thing. If you are adding a rupee with dollar, that is not correct. So in dimensional homogeneity, what you do is you do this. You add a rupee with a rupee. You add a dollar with a dollar. You take the difference of dollars. You should not take the difference of dollar minus rupees. Okay, dollar minus dollar is correct. Rupee minus rupee is correct, but dollar minus rupee is not correct. So dimensional homogeneity, what it says is you should add the units of same uh, units. Okay, you should add the parameters which are having same units. So that's what the dimensional homogeneity is. Okay, so what it demands is it demands something called as consistency in units. Okay, it will be consistent when the units are taken appropriately, when they are added appropriately. Okay, so that consistency should be taken care in case of a dimensional homogeneity. Then we have something called as Buckingham's pi theorem. Buckingham's pi theorem. Okay, this is a bit important. Okay, learn this statement properly, and this statement can come even in your examinations. So I request you to by heart it if possible. So what it says is, if there are n variables in a dimensionally homogeneous equation. What is dimensionally homogeneous? Just now I told you. Okay, consistency should be there for units. Dimensionally homogeneous equation. And if these, if DHESE, if these variables contain m number of primary variables, if it contains m number of primary, where instead of calling it as variable, let me calling it as a dimension. You can call it as a variable also, but dimension would be more appropriate. M primary dimensions, then the variables can be grouped into m minus n, or n minus n. N will be more most of the times. It is n minus m non-dimensional parameters. This is also called as groups, non-dimensional groups. Okay, so this is the statement. And these non-dimensional groups or non-dimensional parameters are called as pi terms. These non-dimensional groups or parameters are called pi terms. That's why the word Buckingham's pi theorem. Okay, these non-dimensional groups are called as pi terms. Okay, so what we have in a given case, there are n variables in dimensionally homogeneous equation, and if these variables contain m primary dimensions, then these variables can be grouped into n minus m non-dimensional parameters. Okay, the meaning of this Buckingham's pi theorem statement you will understand when we solve a problem. For that, let me take a problem, and then you will understand it better. So So here there is a problem. In this problem, you have so many variables here. The variables are mu, rho, the k, cp, and velocity, the delta t, and L. So you have any more units here? You have H1 here. It's not unit, it's variables. Okay, we are speaking about the variables here. So what are all the variables you have here? Mu, rho, k, cp, v, delta t, l, and h. If I number them, how many there? 1, 2, 3, 4, 5, 6, 7, 8. So what is our n here? N is equal to 8 in this question. There are n variables in the questions. Now, what you can do is, if you can group them into m number of m number of what? Primary dimensions. M number of primary dimensions. What are those m number of primary dimensions? Those m number of primary dimensions are these. Okay, so here the primary dimensions in this particular problem can be taken as what? M, L, T, theta, and the H1, the dimension for Q, that is capital H, we have shown here. We have not shown it here. I'm writing it. ML power minus 2, T to the power of minus 2 is actually shown with H. Okay, so let me write that H there. So these are the primary dimensions. How many number are there? 1, 2, 3, 4, 5. So what is M? M is equal to 5. Now what is N minus M? N minus M is equal to 8 minus 5. That is equal to 3. So therefore, these complex 8 terms can be, grouped into three non-dimensional terms. These three terms are called as pi terms. Okay, how do we do that? I will show it to you. Okay, how these three things can be grouped into three terms. I will show it now. So for that, let us take these terms here. The terms here are mu, rho, k, cp, delta t, v, l, and h. These are the 8 things. So for taking this into pi terms, let me define my first pi term. Let me call it as pi 1. For this, what I'm doing is, this is equal to mu into k into v into l. See, mu k v l. This I will call it as core group. Okay, that is the influence of this mu k v l is generally high. Okay, how I say mu k v l is a core group? It is based on experience. Okay, it is based on the experience. You have to tell that is based on the problem. It will vary. So you have to by heart this one. Okay, mu k v l is your core group. Okay, that is your first pi term, and the second pi term will also have this same core group. Third pi term will also have this same core group. Okay, apart from this core group things, let me take the remaining things. See, you have taken mu, you have taken k, you have taken v and l. What are remaining? Rho is remaining. So I will write this rho here. And what is left? Cp is left. And then what is left? 1, 2, 3, 4. See, delta t also should not be taken. Okay, how is this taken? That is also actually based on experience. Okay, what is this experience? This sounds a strange term now for you. But you will understand this as I go forward and reveal the things to you. Okay, CP. Let me write this H. So I'm not going to write the delta T. Why I'm not going to write? Let me explain it as I go forward. Power I am taking. So for all the things A, B, C, D, S power I will take. For the core group, the powers should be taken as A, B, C, D. So now let me take the pi 1 is equal to mu k v l rho, and it has A, B, C, D, S powers. Now let me put the dimensions. Dimension onto the left is taken as 1. Okay, the pi terms will be non-dimensional terms. Okay, pi terms are what? They are non-dimensional terms, so they will not have any units. That's what we will write on your left. Coming to the right, what is the formula for mu? What is the dimensional formula for mu? Let me write all of them also here. For mu, rho, k, cp, delta t, v, l, h. What is the unit for mu? For mu, the unit is Pascal second, that is Newton second per meter square. If you take it in terms of normal terms, it will be turning out to be m L power minus 1 k to the power minus 1. If I take for rho, it is kg per meter cube, it is m into L power minus 3. For Kelvin, it is watt per meter Kelvin. Watt, you can write it as joule per second. If you write it as joule per second, what you have is H L power minus 1 per meter. For K, you have theta to the power minus 1 and T to the power minus 1. Coming to the CP, the unit is joule per kg Kelvin. For joule, you can write H per second is not there here, so L to the power of minus 1 will have. So it's not L to the power of minus 1, it's M to the power of minus 1 because you don't have meter here, you have only kg M power minus 1. For K, it is theta to the power minus 1. For delta T, it is anyways Kelvin, so theta to the power minus theta, you will have theta to the power minus 1, you will not have, it is theta, what you are going to have. And next, moving to your L for sorry, for V, it is meters per second, it is L into T to the power of minus 1. For L, it is M we will write L here. For H, we actually write watt per meter square Kelvin. Watt is joule per second. Joule will represent it with H, and per second you write T to the power of minus 1. For m square, you write L to the power of minus 2. For theta, you write theta to the power minus 1. So these are all the dimensions. Okay. These are units. This is dimensional formula or dimension simply. Okay. So now what you will do is you will substitute these dimensions into these pi terms. Okay. For mu, what is the formula here? Tell me. M L to the power of minus 1, T to the power of minus 1 power A. Coming to K, somebody tell me what is the formula for K? It is H L power minus 1, theta to the power minus 1, and T to the power minus 1 whole to the power of B. And then coming to V, V is L T power minus 1. Let me write it properly. Whole to the power of C. Mu K B is over L. L is simply L to the power of T into the rho. What is the unit for rho? ML power minus 3. Write that here, ML power minus 3. See, what you have to do is you have to actually find out what is the unknown here. Okay, the unknown is ABC. You have to actually calculate the values of ABC using this. You have to compute the values of ABC using this. Okay, if I take M, for M, on the left hand side, there is no unit. So you take the 0 on left hand side. On right hand side, you have A. In A, you have M. So you can write the M here. Also, you have power 1 here. These things you can write here. So what you get here is A plus 1 you will get here. So coming to L, L is anyway 0 on the left hand side. On the other side, where is your L? You have L here, you have L here, you have L here, you have L here. So what you get is here minus A you have, and next you have minus B, next you have plus C, next you have plus D, even here you have it, minus 3 you have. So that is the story of L. Move to the story of T. That is the time. So left hand side anyways it is 0. Moving to the right hand side, what is it? T you have one here, here one, here one. That's it. So you, 3 times it is there. It is minus A here. It is minus B here. It is minus C here. That's it. That's it. So MLT is over. Then let's move to theta. Theta on left hand side is 0. On the right hand side, you have the theta here only. Okay. So it's only there for B. So minus B you will write here. Let's move to H also. For H, it is 0 here. On the other side, H you have only one value here. So it is minus, it's not minus, it's actually plus. Anyways, it's 0, doesn't matter. So if you solve these 5 equations, okay, solving these 5 equations, what you have, solving them, you will understand that B is equal to 0 from these two, from the last two things, and A is equal to minus 1 from the top one. And what will be the values of C and D you need? For that, you have to substitute these values into this T equation. When you substitute that, the C will be, C actually, you got it from this one, the C will be equal to 1 you will get. And these A, B, C you will substitute into this. So from this, you will get the D is equal to 1. So what you understand is from this, you will find out what is your pi term 1. So the pi term 1 is mu to the power of A, then K to the power of B, V to the power of C, L to the power of T into rho is turning into a equation which is having knowns here. The unknowns are A, B, C, D. They are taken as knowns now. So mu to the power of minus 1 and K to the power of B is 0. V to the power of C is 1. L to the power of D is 1. And rho, anyways, is there. Okay. So what I can write is from this pi 1 is nothing but rho VL by mu. Can you see that? What is this? What is this rho VL by mu? Have you seen this equation anywhere?
Reynolds number.
This equation is nothing but a Reynolds number. So what we have done is you have taken a non-dimensional pi term that is your Reynolds number. Now you take the second one, pi 2. What is the pi 2? Mu K V L A B C D into the CP you have taken. Actually, if you solve similarly, what you get is pi 2 is equal to mu power 1 K power minus 1 V power 0 L power 0 into Cp you will get. This is giving you mu Cp by K. See, I have not solved it. You have to solve it for yourself. When you solve it, you will get this equation. That's the point there. Have you seen any kind of this term, mu Cp by K? What is this?
Order number.
This is your Prandtl number. Similarly, you take for pi 3. Pi 3 is equal to mu K V L A B C D in powers into the H. You have solving, what you get is pi 2 is equal to sorry, this is pi 3 mu to the power of 0 and k to the power of minus 1 v to the power of 0 l l to the power of 1 and h you will get. So what to get here is HL by K. What is this formula?
Russell
This
number.
is
Russell.
Nusselt number formula. See what we have done. We have taken n terms here, n variables here. Okay, there are 8 variables, and we have taken 5 primary dimensions here. These are the 5 primary dimensions. So n minus m is 3. That is 3 pi terms we got. What are those 3 pi terms? They are Reynolds number, Prandtl number, and the Nusselt number. So what you are doing is you are saying that here, whatever the case is there, it is a function of the Reynolds number, the Prandtl number, and the Nusselt number, which is equal to 0, or you can write it like Nusselt number as a function of Reynolds into Reynolds and the Prandtl. So how did we get this Dittus-Boelter equation or all the equations that you have in forced convection or in case of natural convection? This is the procedure followed. Okay, this is the help your Buckingham's pi theorem is giving you to actually properly non-dimensionalize the things. Okay, that's why I did not tell you this in the beginning. Okay, generally people will teach the Buckingham's pi theorem first and then move to the explanation on the external flow, the non-correlated, non-dimensional terms and correlations, etc. Okay, but I have done it reverse so that it will be easy for you to understand. Okay, if I say it in the beginning, you will not understand anything actually. Okay, there are so many uh, assumptions, apprehensions. Why those assumptions are taken here? Okay, why I have taken MuKVL as a core group? Because I know the results. Okay, this is what I generally obtain. So what is my result is partially known to me. Exactly is not known to me. So based on that partial knowledge, I will take my core group. So similarly, how did I neglect the delta t here? Because the delta t influence is very much less in this case of this one or this delta t effect is actually taken in H. All these things can be correlated and explained. Anyways, ultimately you should get this one in your exam when this particular question is given. Okay, this same question can also be given this way. Okay, how you will solve the same procedure you will follow. Okay, this is also the same question. So this is how Buckingham's pi theorem will help you relate between the terms. Okay. This question, same answer. You will write. Okay. So that's the thing with your second problem also. So moving to the third one. I hope is it it's clear. If you have any questions, you can ask. Definitely, you will have questions here at this level. This is bit, it would seem complex at the first level, but if you solve it for yourself, you will find it easy. Okay. My request for all of you is you follow heat and mass transfer textbook by D.S. Kumar. D.S. Kumar. For this topic only, I'm telling, because this topic is given very much clearly in this particular textbook. So if you follow this textbook, dimensional analysis will be very clear to you. Okay. So that's the thing. Have any questions? You can definitely ask now itself. No questions. Okay, let me move on. You have questions? You can ask me at the later stage also. See, here you have one more thing. This is also a similar kind of a thing. So here he is giving a case for natural convection and asking you to do it. Okay. So what you have to do, you have to take the appropriate numbers here. This is 1, 2, 3, 4, 5. See, beta G is taken as one term. So this is the sixth term, and the delta T is taken as the seventh term. This is taken as the eighth term. So what is n here? N is equal to 8. What is your m? You have to get it. For getting your m, you have 1 mass, length 2, time 3, temperature as your fourth one. And what is the fifth one? You should have heat flow. Okay. So the m is equal to 5. So n minus m is equal to what? 8 minus 5. 8 minus 5 is equal to what? 3. Three-dimensional groups can be obtained here. What are those three-dimensional, non-dimensional groups? Those non-dimensional group are, one is Nusselt number group, the second one is Prandtl number group, the third one is Grashof number group. Okay, you know the answer already. So that's the point. Okay, so what you do is you will actually take one core group like you have taken for the previous thing. So beta G is taken as one parameter, and here the pi term you need to practice. If you don't practice for the pi terms, you will definitely do it wrong in the examination. So mu power mu k into beta G into delta T into L into rho is taken here. See, this is A, power B, power C, power D. The difference here is beta G into delta T is taken as one term here. Okay, or power C is given or taken in combination. That's the point. That will be taken as a core group. And pi 2 term is mu k into beta G into delta T into L. This is again a core group A, B, C, D. And the remaining thing is here pi 3 mu k beta G into delta T to the power of C, D, E, A, L also should be here. See, this is the core group I have written in pi 2 and pi 3. Here you will have Cp coming up, and here you will have H coming up. Okay. So if you take these pi terms and solve for, ultimately what you have to get is you have to get these non-dimensional terms here. There's a Nusselt number, the Prandtl number, and the Grashof number. You have to get if this is a natural convection thing. If it is forced convection thing, you have to follow the procedure that I have said just now. Okay. If you have any more doubts, you can ask, or I will move forward. Right. Moving forward, what is left in our syllabus is just a classification. This classification is quite simple. The classification you have actually studied in your fluid mechanics. Classification based on flow is already known to you. It's not a great thing. First thing I would like to tell is viscous versus non-viscous, or this non-viscous is also called as inviscid. Inviscid, non-viscous flow. Okay, so this is the first kind of classification I'm taking. Okay, the flow is viscous. Well, the viscosity has to be considered during the analysis. You will consider the viscosity. When you say that the flow is inviscid, you will not consider the effect of the viscosity. That is the thing here. And moving to the second kind of classification, you have internal flow versus the external flow. You know this already. Internal means inside a tube it is flowing, and external flow means it is over a body, it is flowing. Then third one, compressible flow versus the incompressible flow. So compressible means the density is not constant, whereas incompressible density is constant. That's what the compressible versus incompressible. Coming to the fourth one, the laminar versus turbulent. Okay, you know what is laminar? Laminar means the flow is very smooth, and when it comes to turbulent, the flow is very vibrant or rough, you can say. Okay, it flows in a orderly fashion here. Here, haphazard manner, the flow will be there. And coming to the next one, we will have natural flow versus the forced flow. Like a natural convection or the forced convection sort of. You know this already. And next one is steady versus unsteady. Okay, similar kind of thing is uniform versus non-uniform. Okay, in steady, the property will not vary with time. In unsteady, the property will vary with time. In uniform, the property will not vary with position. Non-uniform will vary with the position. Okay, this is based on time, and this is based on location or place, you can say. So that's the thing regarding steady. And one more kind of classification is 1D flow, 2D flow, 3D flow. Okay. So these are all the various classifications. This is quite simple. You will study about this classification even in your fluid mechanics. So that's quite simple. So